Identify the polyhedron. This is a polyhedron we're considering. And notice it's a three-dimensional figure. There's length, width, and depth. This one's called a pentagonal prism. The pentagonal part of the name comes from the type of base we have. We have a pentagon up here and a pentagon down here. These bases are pentagons. So that's where the pentagonal part of the name comes from. The prism part of the name comes from these two bases being parallel. That's what makes it a prism. Now some definitions. A polyhedron, or polyhedra in the plural, is a simple closed surface made of polygonal regions or faces. A prism is a polyhedron in which two congruent polygonal faces or bases lie in parallel planes. The relationship between the number of faces, the number of edges, and the number of vertices of any polyhedron is described by this equation. So let's go back to our polygonal prism and identify the edges. The edges are the outline. So here's an edge, here's an edge, here's an edge. All of these are edges. These corners are called vertices. So there's many vertices here. And the faces are what's on the surface. Here's a face, here's a face, there's a face underneath, there's a face on the top, on the sides. Now let's go back to our equation. So this equation describes a relationship between the vertices, the faces, and the edges. It turns out to be that each time you plug in the number of vertices, the number of faces, and the number of edges, and you do this side of the equation, it's always going to give you a 2. So let's verify this equation. So for our problem, the pentagonal prism, there are 10 vertices, 7 faces, and we could count 15 edges. So you replace each one of these variables, the vertice, the face, and the edge variables with their numbers. And if you work this out, it will give you a 2 the way the formula says. So we have proven, using a concrete example with numbers, vertices, faces, and edges, that this equation is in fact true for any polyhedron.